Hello everyone. In this video we are going to learn section 2 of chapter 6. First, let's remember what we learned in our previous lesson. In our previous lesson we learned how to produce first few terms if general formula is given, and if first few terms are given, how to express general formula. In this lesson we are going to learn how to write some of the terms in the sequence and how to evaluate them. So here are some examples. So the first sequence here is 1, 2, 3, 4. That's sequence. The series means sum of the terms in the sequence. So it means 1 plus 2 plus 3 plus 4. So the sum means series. A series can also be represented by using summation notation, which uses the Greek letter capital sigma to denote the sum of the sequences defined by a rule, as shown. So here you see capital sigma. Underneath it you have k equals 1, that's the first value of k. Above it you have 5, that's the last value of k. And right next to it you have 2k, which is explicit formula for the sequence. So this entire thing is called series. So the first part of the section is writing sequences by using writing series by using summation notation. So we are given the sequence. First we are going to identify the explicit formula and then write by using summation notation. So here we have 4, 8, 12, 16, 20. So as I see here, we have multiples of 4. So you can say that your explicit formula is 4k, multiples of 4. So your explicit formula is 4k. So how are we going to write the summation notation? So let's use capital sigma first. And then the first value of k is 1, because 4 times 1 is 4. So it is 1. And the last number for k is 5, because the last value here in the sequence is 20. So 4 times 5 is 20. So from 1 to 5, you have 4k. So you can read this as summation k going from 1 to 5 of 4k. Or you can read it as the sum k from 1 to 5 of 4k. Let's take a look at another example. How are we gonna write it by using summation notation? The first thing we're gonna do is identifying the pattern. So what's the pattern here? So as I see in numerator, we have constant number, which is 2. So numerator is 2. Your denominator, I see here in denominator, successive perfect square numbers. So here we have 2 squared, which is 4, 3 squared, which is 9, 4 squared, 5 squared, 6 squared. So we have successive perfect squares here. So we write the explicit formula as 2 over k squared. So what about summation notation? So let's put the capital sigma and then put 2 over k squared right next to it. So what is the lowest value of k? Let's try. If it is 1, it is 2 over 1 squared, which is not true. Our first term is 2 over 4, which means our first number for k is 2. So it's 2 over 2 squared, that's true. 2 over 3 squared, yes. 2 over 4 squared, 2 over 16, yes, that's true. 2 over 5 squared, 2 over 25, and 2 over 6 squared, 2 over 36. So the first value for k is 2, last value for the k is 6. Here is how you write the sum by using summation notation. So this type notation is very condensed way of saying that 2 over 4 plus 2 over 9 plus 2 over 16 plus 2 over 25 plus 2 over 36. So that's a short way of writing the sum. Next question. So here I see negative 2, 4, negative 6, 8, and negative 10. So first, when I look at the sum, I see here even numbers, but some of them has negative in front. So I can say that my explicit formula is 2k, but there's something in front. that represents that some of the terms are negative. So 2k, in front of 2k I have negative 1 raised to power k. What does that mean? So when I start with number 1, so negative 1 to the power of 1 times 2 times 1 is negative 2, so yeah, that's true. Let's try number 2. So negative 1 squared times 2 times 2 positive 4. Yes, that's true. And so on. So here is the explicit formula that must be written right next to sigma notation. So the lowest number for k is 1. The highest number for k is 5 because the last term is 10. So when you plug them back into them, you'll see that it works. So this was the first part of the section. Writing the sum by using summation notation. The second part of the section is evaluating series. That's easier than the first part because you don't have to generate the formula. It's already given. Everything is given. You just have to write the sum in a long way. That's written in a short way. So you will do the reverse now. You're going to write them in a long way. We're going to do the opposite here. So what is the first thing we're going to do? You are going to substitute numbers from 2 to 5 one by one for k and add them up. So the first number here is 2, so 1 over 3 squared, plus second number is 3, 1 over 3 cubed, plus third number is 4, 1 over 3 to the 4, plus the last number is 5, 1 over 3 to the 5. So we expand the series and add them up, evaluate, simplify. The result becomes 40 over 243. Let's take a look at another example. Similarly, we are given the formula with the sigma notation. So we're going to expand it by substituting numbers from 1 to 6 one by one for k and adding them up. So the first number is 1. So it's 1 squared minus 10 plus second number is 2, 2 squared minus 10 plus 3 squared minus 10 plus 4 squared minus 10 plus 5 squared minus 10 plus last number is 6, 6 squared minus 10. You're going to expand them, evaluate them and simplify them. The result becomes 31. So that's it for the second part. Now let's move on the third part. In the third part we have some formulas. Here we have a constant term. We have 3, a constant number. So from 1 to 5, every value is 3. So for 1 for k, we have 3. 2 for k, we have 3. 3 for k, we have 3. 4 for k, we have 3. 5 for k, we have 3. So we have 5 3's here. So we can write this as 3 multiplied by number of terms in the sequence. How many numbers do we have in the sequence? Here we have 5 numbers. So 5 times 3, 15. So the easy way here is the formula. The formula is given as the constant number multiplied by the number of terms in the sequence. So C multiplied by N. N is the number of terms in the sequence, so N times C for constant series. So same goes for linear sequences. Here we have linear sequence, the sum of numbers from 1 to 10. It's pretty long. You don't want to do that. So we have an easy way of doing that. So the formula here is n times n plus 1 over 2. N is the last value for k. So the last value for k here in the question is 10. So the answer will be 10 plus 1 over 10 times 10 plus 1 over 2. So it's an easy way of writing the sum. So the same goes for quadratic series. We have also formula for quadratic series. So let's see all those formulas at once. So here is the constant series formula, the sum of constant series, sum of linear series formula, and sum of quadratic series formula. So in this last part, let's solve some examples by using these formulas. The first example here is sum of k going from 4 to 10 of 6. So we have a constant series here. So let's apply the formula. The formula here is the number in the series, the constant number here is 6 multiplied by number of numbers in the series, which is 7. So it's 42. That's the first way. The second way, we can write it in a long way. Here you are. So you can find the result. In both of the ways you find the result, but the formula is much more easier and faster. Next one. Here I see k, which means it's a linear series. So let's apply the formula. N times n plus 1 over 2. What is n? N is the last value of k, which is 8 here. So 8 times 8 plus 1 over 2, which is 36. That's the first way. The second way is the long way. Write them down one by one and evaluate it. Last question we're going to look at is a quadratic series. So let's apply the formula for quadratic series. N times n plus 1 times 2n plus 1 over 2. So your n is the last number for k, which is 12. So 12 times 12 plus 1 times 2 times 12 plus 1 over 2. Let's evaluate that, simplify that, and the result becomes 650.